Energy and Atmosphere Prerequisite Fundamental Refrigerant Management. The intent of this prerequisite is to reduce stratospheric ozone depletion. No CFC-based refrigerants, and you have to either have them out of the building or have a replacement plan for equipment that is using the CFCs, such as R11 or R12. Existing small HVAC and R units, defined as containing less than 0.5 pounds, 225 grams of refrigerant, and other equipment such as standard refrigerators, small water coolers, and any other equipment that contains less than 0.5 pounds, 225 grams of refrigerant, are exempt. The EPA set regulations on using and recycling ozone-depleting compounds as part of the Clean Air Act. Project teams must adhere to this standard to minimize refrigerant leakage for systems with existing CFC-containing equipment. New construction projects cannot install new CFC-based refrigeration due to the Montreal Protocol, which phased out CFCs for industrialized nations in 1995. However, CFCs may still be used in existing HVAC equipment prior to either 1995 in developed countries or 2010 in developing countries. The fact of the matter is, many of us are dealing with existing buildings which have existing CFC-based refrigerant systems. The operations and maintenance staff should identify all HVAC and equipment that uses refrigerants. Ensure proper maintenance on systems to minimize leakage and replace or retrofit existing CFC-based equipment. There are exceptions if a third-party audit shows that system replacement or conversion is not economically feasible, or unless a phase-out plan for CFC-based refrigerants is in place. The replacement or conversion of HVAC and R equipment is considered not economically feasible if the simple payback of the replacement or conversion is greater than 10 years per the equation shown. If CFC-based refrigerants are maintained in the building, reduce annual leakage to 5% or less using the procedures in the Clean Air Act, Title VI, Rule 608, governing refrigerant management and reporting, or a local equivalent for projects outside the U.S., and reduce the total leakage over the remaining life of the unit to less than 30% of its refrigerant charge. Energy and Atmosphere Credit Enhanced Refrigerant Management. This credit is worth 1 point. The intent of this credit is to reduce ozone depletion and support early compliance with the Montreal Protocol while minimizing direct contributions to climate change. Fundamental refrigerant management is pretty clean-cut. Use no CFC-based refrigerants and have a phase-out plan for existing buildings. When it comes to advanced refrigerant management, you have a couple of options. One, you can forego refrigerants altogether, or you can use very low-impact options, like, for example, water. That's not particularly common in existing buildings unless maybe they're small and quite old. Most projects end up following option 2, which has you plug in all of the data about your refrigerant-using equipment. What the full charge is, what refrigerant type you're using, lifespan of the equipment, etc., and it will turn out a number of your overall refrigerant impact. Enhanced refrigerant management has 2 options. Option 1, no refrigerants or low-impact refrigerants can earn 1 point. Or Option 2, calculations of refrigerant impact can earn 1 point. Option 1 is to not use refrigerants at all, or naturally occurring or synthetic refrigerants. This is a great simple option, but it is rarely done, except in cases where a building is in a very supportive climate region. Option 2 is selecting equipment with a combination of low ODP, ozone depleting potential, and GWP, global warming potential. The table here shows some of the available refrigerants and their ODP and GWP values. The refrigerant impacts, along with the expected equipment life, can be used to calculate the impact of the proposed system design. Equipment is assumed to have a life of 10 years, a leakage rate of 2% per year, and end-of-life refrigerant loss of 10%. These values, along with the refrigerant charge, are plugged into some formulas to determine the impact. The refrigerant charge is the ratio of the total refrigerant used to the cooling capacity, measuring in pounds per ton or kilograms per kilowatt. You might ask, well, what's the limit to this? Do I need to look at my refrigerator and see what kind of refrigerant that's using? Small HVAC units with anything less than a half a pound of refrigerant are excluded. This exclusion gives you some parameters about those wall units that you may have in the window or kitchen refrigerators. The combination of all new and existing base building and tenant HVAC&R equipment that serve the project must comply with the requirements. That's key. If a tenant installs their own HVAC unit on the rooftop to cool their own computer closet in the building, and the HVAC unit doesn't comply, the project can't earn this credit. Choose natural refrigerants. If you can't use CFCs, what can you use? There are options, but it's going to take some work and a great design to do the calculations to make sure this works and will serve the building occupants. Coordinate with a mechanical engineer to select the proper refrigerants and minimize refrigerant leakage. Other manufacturers won't talk about the leakage rates. What you have to do is have someone come back and verify the leakage rates in order to achieve enhanced refrigerant management. This is something you wouldn't necessarily just get signed off on from the manufacturer, but something that would require follow-up in commissioning. Some alternative systems for fire suppression, direct energy systems, and systems with a long service life. Window air conditioning units and heat pumps have service lives of 10 years. Unitary, split, and packaged air conditioning units and heat pumps have service lives of 15 years. Reciprocating compressors and reciprocating chillers have service lives of 20 years. Centrifugal and absorption chillers have service lives of 23 years. If you have a retail project, there is an option to follow for some kinds of retail commercial refrigeration equipment. These more restrictive guidelines have been established through the U.S. EPA Green Program. For the next credits, there's a suite of them related to existing building commissioning. This is very similar to how these credits worked in 2009. Commissioning optimizes the energy-consuming building systems, getting them running better and saving electricity and thus operating costs. EA credit, existing building commissioning, analysis. This credit is worth 2 points. A critical part of the team will be the commissioning agent. The intent is to use the existing building commissioning process to improve building operations, energy, and resource efficiency. For establishment, there are 2 options for this credit. Either option will earn 2 points. Option 1, existing building commissioning. Option 2, energy audit. Basically, you're building on that energy audit you did in the prerequisite to do a more thorough analysis of energy conservation measures that may exist in your building. You can choose either a true existing building commissioning process, which involves things like functional testing of the equipment, or you can do a Level 2 energy audit, which is a more involved, thorough version of the audit that was done for the prerequisite. Generally, you will use an audit if you know that you have some requirements that is near the end of its life, and you want to figure out the best kind of strategy for replacing it, or if you know there are other types of capital projects you want to take on. Commissioning is really good when you have good equipment, but it has complicated controls, and you would see some benefit from testing it to making sure it's functioning as intended. That can help govern which of these 2 options you choose. Option 1, Existing Building Commissioning, requires developing an existing building commissioning plan to effectively inventory and evaluate specific opportunities within the systems being analyzed. The commissioning plan must include the following: updated current facilities requirements, the commissioning team members and their roles and responsibilities during the commissioning process, a description of the approach for identifying and analyzing facility improvement opportunities, the process for reviewing and prioritizing identified opportunities with the owner and developing an implementation plan, the format and content of the eventual deliverables from the commissioning process, and the proposed schedule. During the performance period, the project team will execute the plan. Option 2 is an ASHRAE Level 2 energy audit. For this option, you will be developing an energy audit plan following the requirements of ASHRAE Level 2, Energy Survey and Analysis, to evaluate efficiency opportunities. The audit plan must include the following: the audit team members and their roles and responsibilities during the audit process, a description of the approach for identifying and analyzing facility improvement opportunities, the process for reviewing and prioritizing identified opportunities with the owner and developing an implementation plan, the format and content of the eventual deliverables from the audit process, the proposed schedule, and effective energy savings. During the performance period, the project team will execute the plan. Remember that EA Prerequisite Energy Efficiency Best Management Practices uses an ASHRAE Level 1 audit walkthrough. EA Credit Existing Building Commissioning Analysis uses an ASHRAE Level 2 energy audit. Building systems that do not operate properly waste energy, which then has an environmental chain reaction leading to increased energy production and occupant discomfort. Retro commissioning reduces operating costs, protects or enhances property value, and reduces the frequency of replacement and repair of the equipment. Commissioning helps with the reduction in the release of harmful emissions, a reduced need for natural resource extraction, and reducing operating costs of equipment. Referenced standards. ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. The reference standard for this credit is an ASHRAE Level 2 Energy Audit, Energy Survey, and Analysis. For the implementation, you're going to build off that CFR, Current Facilities Requirements, and the other plan that we mapped out in the prerequisite. You're going to fine-tune your energy use breakdown by end use and come up with your strategy for further evaluating energy conservation measures. You do not have to perform any of your findings for this credit. You just have to do either the commissioning or the audit. The next credit rewards you for actually putting into place some of the findings that came out of that earlier credit. You have to implement all the new low-cost improvements that were identified and develop a longer-term plan for more capital-intensive improvements. Option 1 is to develop an existing building commissioning plan for the building's major energy-using systems. This phase of the commissioning process draws careful attention to all aspects of the current operations and maintenance program, including equipment, practices, procedures, and the interaction of the program as a whole with building occupants and their use in the building. The steps include a site assessment, recording the energy use breakdown of the systems, diagnostic monitoring and functional testing, creating a master list of findings. This master list is the most important deliverable, as it identifies anything affecting occupant comfort, energy use, and any problem identified. Option 2 is to conduct an energy audit that meets the requirements of ASHRAE Level 2. This survey includes a cost-benefit analysis and identifies any capital improvements. This audit locates the opportunities for energy savings. The required calculations are detailed in the reference standard ASHRAE procedures for commercial building energy audits. The investigation and analysis can take place before the performance period, but it's recommended to do it during the performance period. EA Credit, Existing Building Commissioning, Implementation. This credit is worth 2 points. There is no exemplary performance. The intent is to use the existing building commissioning process to improve building operations, energy, and resource efficiency. For this credit, implement no or low-cost operational improvements. Create a capital plan for major retrofits or upgrades. Provide training for management staff. Show any changes in costs and benefits due to the implementation. Update the operations and maintenance plan and current facilities requirements. The previous credit helped to investigate and identify areas for improvement. For this credit, you have to implement the improvements. Project teams are still implementing and upgrading systems and dealing with energy efficiency as a result of improved commissioning practices. Whatever was investigated and deemed appropriate in EA Prerequisite Energy Efficiency Best Management Practices carries over and can now be implemented. Complete no or low-cost improvements during the performance period. Provide a cost-benefit analysis for each measure, and develop a capital plan for major retrofits and upgrades that will not be implemented now. Any plan for capital improvements must be in place by the end of the performance period. The only calculation is the simple payback period calculation. The simple payback period calculation is equal to a year's project cost in dollars divided by annual operating savings in dollars. Remember, for LEED online uploads, teams have to track the no and low-cost improvements and minor repairs that were implemented during the performance period, as well as update the operations and maintenance plan. You do have a project team or building owner. You work with your auditor, your agent, so the items that are on the list that they produced meet certain criteria you have. You're not beholden to do something that doesn't make sense for your building or doesn't meet your cost criteria. That would all be hashed out in the auditing or commissioning process. It's pretty uncommon for a team to pursue that earlier credit and not also go ahead and get this credit because you basically uncovered some good ideas for saving money. Now you get some other points if you go in and implement those ideas. When you're creating your 5-year plan, you want to be somewhat detailed and have a timeline indication of where the capital resources are going to come to put this plan into action. Some no and low-cost examples may include reducing consumption using an existing BAS and domestic hot water heater upgrades. D-lamp or relamp interior lighting. That may mean reducing the number of lamps in your fixtures or relamping with more efficient T8s or T5s. Replace manual thermostats with programmable thermostats in designated rooms. Optimize start and stop times for your air handlers and fix any duct leaks. EA Credit, Ongoing Commissioning. For our commissioning credits, there are 2 points for investigating, 2 points for implementing, and now for EA Credit Ongoing Commissioning, there are 3 points. There is no exemplary performance option. The intent is to use the existing building commissioning process to improve building operations, energy, and resource efficiency. This requires teams to commit to repeating a commissioning cycle every couple of years, especially for buildings that have complex systems and elaborate automation systems. This could be a very appropriate way to stay on top of system performance over time. There would be updates to your ongoing commissioning plan over time. You also need to make sure that people understand what their role is intended to be. Oftentimes, this is a mix of internal resources to the building and external third-party people. So you really need to have it determined who is in charge and of what. Once you've done all of that, you not only have a testing plan, but also a strategy for correcting deficiencies that are covered during the ongoing commissioning. There may be an occasional need to update the associated documentation, the CRF, And you'll also want to leave a paper record of the completion of the commissioning cycle. Implement an ongoing commissioning program that includes elements of planning, system testing, performance verification, corrective action response, ongoing measurement, documentation to solve operating problems. In addition, write a plan that summarizes the commissioning cycle for the building by equipment or building systems group. The ongoing commissioning cycle must not exceed 24 months. You have to complete at least half of the scope of work in the first commissioning cycle. Be sure to update the building operating plan and/or systems narrative as necessary to reflect any changes that may occur. Implementation. The ongoing commissioning plan is in place when documentation is submitted and when the project team promises to do the ongoing commissioning within 24 months. Ongoing commissioning takes a systems-wide approach and ensures that the indoor conditions and energy power of the building systems are understood, monitored, and repaired. It is based on performance testing and data that illustrate how the system is functioning, and it identifies opportunities for improvement. This is different from preventive maintenance. The plan should include equipment that's going to be commissioned, the frequency, and the performance tasks. Make sure indoor conditions in energy-based systems are running properly and maintained. A commissioning agent may have done the retro commissioning and developed this ongoing commissioning plan, but the building engineer should more than likely be able to complete the ongoing commissioning. How much time will it take? It really depends on each individual building, because some buildings might be a 200,000 square foot building. One building that's that size might have 8 air handlers, and the other one might have 2 air handlers. The equipment count and complexity really factors into how difficult it is to get through all the right functional testing. Usually, at the outset of a plan, you'll develop this big equipment list. You might figure out an appropriate sampling so you don't test 100% of the VAV boxes. Maybe you do 1/3 every year for 3 years, and you map the estimated amount of time per test per piece of equipment to get that time budget. That's the same way that a commissioning agent would figure out what their costs are going to be if you outsource it, and you can apply that to your strategy planning for a building engineer's time. Some of the things that we've already talked about, like using the janitorial staff as agents in energy and water conservation, helps the project. There's also investing in your operators. Just a modicum of what you invest in new fancy equipment would be such a leg up. It's crazy that a building owner might spend hundreds of thousands or even millions of dollars on this fancy equipment, but then will begrudge the operators a few $1,000s a year in education and training budget, so they can really become skillful at using this fancy, expensive equipment. You're sort of shooting yourself in the foot with that kind of strategy, but it really is quite common. Operator training is insurance to guarantee the value that you've already put into your systems. One of the most successful ways of reducing energy cost in office buildings is to work very closely with the engineers and with the operators, making sure that they're well trained and staying on top of the operations. The other way is to put in automated devices. Here's an example. Even the most energy-conscious folks at an office, for example, will typically leave their monitors on at night. They think they're off because the screen goes dark, but they're still on. You need to install devices that sense the inactivity, and devices will cut off the power. The best-case scenario is general good technology paired with trained and attentive people. If you have technology and nobody cares, a lot of times that technology will go haywire, and there's no one to correct it. You're worse than where you started. Or you have passive systems where it's okay if nobody's engaged. Either way, having the people involved is what's going to yield the best results. Energy and atmosphere credit, demand response. The intent of this credit is to increase participation in demand response technologies and programs that make energy generation and distribution systems more efficient, increase grid reliability, and reduce greenhouse gas emissions. The credit can earn up to 3 points. Demand response is a new credit in LEED v4. The official definition of demand response is a change in electricity use by demand-side resources from their normal consumption patterns in response to changes in the price of electricity or to incentive payments designed to induce lower electricity use at times of high wholesale market prices or when system reliability is jeopardized. A simplified definition is demand response is a matter of balancing customers' need for electricity with the power company's output. You're trying to shed the energy during peak demand. When you turn on an appliance, you expect immediate results. You don't wait for a light bulb to come on after you've flipped the switch. Electricity isn't stored in a tank in your yard. So when you need it now, how does it deliver? That's the power grid at work. Electricity is generated at a power plant and transmitted to local substations where transformers turn it into usable voltage. Then it's distributed into our homes and businesses through a web of high-voltage transmission lines, the grid. From day to day, electricity consumers use a predictable minimum amount of power, called the base load. At the very least, the grid needs to handle this scheduled energy production in addition to any usage spikes that happen. Demand for electricity is typically highest in the afternoon and early evening, as well as during the summertime when air conditioners run day and night. When many people want to use their electrical appliances at the same time, it's called peak usage time. Until your power is knocked out, you probably don't pay much attention to how often you turn on a light or the television or what time of day you do it. When you flip on a light switch, electricity travels in an instant to your home and the bulb glows. That's called demand. When millions of electricity customers all turn on their air conditioners after work, it increases the demand load on the grid. Our demand for electricity is growing, and the Energy Information Administration estimates that demand will rise at least 40% by 2030. The power grid supplies only the electricity we ask for, though, and it's up to us to practice energy conservation. One way to decrease the demand load is a concept called demand response. In broad terms, demand response programs give us, residential, commercial, and industrial consumers, the ability to voluntarily trim our electricity usage at specific times of the day, such as peak hours, during high electricity prices, or during emergencies, such as preventing a blackout. Case 1 can earn 2 points and is for projects located in an area where the utility company offers a demand response program. Demand response is still relatively new, so it isn't available everywhere. Case 2 can earn 1 point and is for projects located in an area without a demand response program available. Case 3 can earn 2 points for permanent load shifting. Case 1 requires a project to participate in a demand response program. There are several activities that have to be completed. Design a system with the capability for real-time, fully automated DR based on external initiation by a DR program provider. Semi-automated DR may be utilized in practice. Enroll in a minimum 1-year DR participation amount contractual commitment with a qualified DR program provider with the intention of multi-year renewal for at least 10% of the estimated peak electricity demand. Peak demand is determined under EA prerequisite minimum energy performance. Develop a comprehensive plan for meeting the contractual commitment during a demand response event. Include the DR processes in the scope of work for the commissioning authority, including participation in at least one full test of the DR plan. That is your key information here. Participate in a program and develop a comprehensive plan for shedding at least 10% of the building's estimated peak electric usage. Case 2 requires designing the building in a manner that enables it to participate in a demand response program. Projects have to install recording meters, develop a load shedding plan, include the system in commissioning, and contact utility representatives to discuss future DR programs. Basically, you are getting the building ready for a program, if and when the program is released by the utility company. Case 3 is for permanent load shifting. Implement electrical load shifting measures with the following requirements. Have in place, during the performance period, a system which permanently transfers electricity demand from peak hours to off-peak hours as defined by the local utility provider. Demonstrate that the facility is successfully reducing peak demand by 10% during the performance period as compared to peak electrical demand by identifying all load shifting measures and their intended peak electrical load shift, verifying a corresponding peak electrical load reduction for each measure, verifying a corresponding off-peak electrical load increase for each measure. Include the load shifting measures in the current facility's requirements and operations and maintenance plan. Demand response systems can be manual, semi-automated, or fully automated. LEED does not allow projects to use a manual system. That's important to remember. Manual systems involve intensive human intervention to activate, and consequently are used in situations where the primary goal is to shed load during times of peak usage. More advanced uses of demand response, such as systematically shifting load to off-peak times, require some form of automation, and consequently the installation of an Energy Management Control System, EMCS, or Building Automation System, BAS. BAS is a demand response tool that allows building managers to program the building's equipment and appliances in such a way that they automatically power down in response to peak load events, reducing the building's load demand in times of peak usage and/or peak pricing. While many commercial buildings are equipped with technology to facilitate fully automated demand response, very few actually operate in a manner that achieves their true potential in terms of demand response and energy efficiency. Manual demand response does not use a BAS. People manually turn off lights and equipment when asked to do so. This is not an option for LEED. Semi-automated demand response uses a BAS. A person initiates a control strategy pre-programmed into the BAS when a demand response event is called. Fully automated demand response, AutoDR, also uses a BAS. Receipt of an external price, reliability, or event signal automatically triggers a BAS control sequence that switches the building to low power mode. No human intervention is required. Demand response is something you will need to contact your utility provider about early on to see if a program is available. The minimum reduction is 10% in peak electricity demand, so the project team will need to review the energy model from EA Prerequisite Minimum Energy Performance to determine what quantity that will be. If a project used the prescriptive paths for the prerequisite, this credit can still be earned. In these cases, projects can use space peak load calculations to estimate the peak demand. Energy and atmosphere credit, renewable energy, and carbon offsets. The intent of this credit is to reduce the environmental and economic harms associated with fossil fuel energy by increasing self-supply of renewable energy. On-site renewable energy systems offset building energy costs. Your building may not become more efficient, but you reduce the cost of energy. Additionally, you get to reduce the carbon emissions that are associated with the building because the power that the building has probably comes from coal or other brown energy sources. Using a cleaner energy source reduces the carbon footprint for the building. For establishment, demonstrate one or both of the following for at least a portion of the building's total energy use. Total energy use is met directly with renewable energy systems. A minimum 2-year contract is in place with the commitment to renew on an ongoing basis to purchase qualified resources that will be delivered at least annually. Resources must have come online after January 1, 2005. For performance, meet at least some of the building's total energy use directly with renewable energy systems, or engage in a contract to purchase green power, carbon offsets, or renewable energy certificates, RECs. Green power and RECs must be Green E Energy certified or the equivalent. RECs can be used only to mitigate the effects of Scope 2 electricity use. Carbon offsets may be used to mitigate Scope 1 or Scope 2 emissions on a metric ton of carbon dioxide equivalent basis and must be Green E Climate certified or the equivalent. For U.S. projects, the offsets must come from greenhouse gas emissions reduction projects within the U.S. Use the following equation to calculate credit up to the 5-point limit. The renewable energy produced is expressed as a percent of the annual energy cost. What people generally do is look at their total building energy performance, then look at how much renewable energy they're producing, and calculate a percentage. The CBECS database will help determine these values if the project team didn't do a whole building energy simulation. For implementation, identify what the building's energy use is, determine which techniques are most adequate, and then install the systems. Eligible on-site systems for this credit include photovoltaic systems, wind energy systems, solar thermal systems, biofuel-based electrical systems, geothermal heating systems, geothermal electric systems, low-impact hydroelectric systems, wave and tidal power systems, some geothermal systems. Generally, projects undersize their renewable energy systems. If you can oversize the systems and become a power supplier to your local energy provider, then the system becomes a small profit center. It's important for you to know what on-site systems are eligible. Some biofuels that can't be included are burning trash, forest biomass other than mill residue, wood covered with paints and coatings, preserved wood such as pressure-treated lumber. Those biofuels that are not eligible have a high greenhouse gas potential or toxicity potential. Systems such as architectural features, passive solar, daylighting, and ground source heat pumps, while they do save energy, do not count towards this credit. Those design strategies are rewarded in minimizing energy consumption. The points for renewable energy are calculated by dividing the renewable energy generated by the total building energy use and dividing that by 1.5%. Consider that this is a contract. This contract is distinct from other strategies because the other strategies are designed and implemented on your site. What this is saying is that you are engaging in a contract with a renewable electricity provider. This is also factoring all of the energy used in the building, not just the electric energy use. If your building uses natural gas for heat in the winter, you are calculating that usage too. Green power and carbon offsets are calculated based on the energy consumed by the project. Setting your project's offset goals. For the credit, the building owner is looking at a long-term commitment to earn this credit, at least 2 years. This credit is not a one-time purchase, it is a yearly purchase for a minimum of 2 years. That is something to consider when deciding to pursue this credit. What is green power? Not to be confused with on-site renewable energy production. Green power is a subset of renewable energy composed of grid-based electricity produced from renewable energy sources. New in LEED v4 is any qualified resources must have come online since January 1, 2005. Go to greene.org and you can get a pretty good idea of how green power works for this credit. The idea is your electricity provider is providing power from the grid. Probably 95% of it is from brown sources, and maybe 5% of it is from green sources. What you are doing by purchasing at least 25% of your power over 2 years from a Greene provider is you are subsidizing green power. What you're paying is actually not just for power from them, you're paying for the difference for them to provide this power to the grid. The provider is not plugging green power into your building. You're subsidizing them providing green power to the grid. Referenced standards. Any green power and RECs must be certified by Greene. Carbon offsets must be Greene climate certified or an equivalent. For carbon offsets, the total emissions is the primary metric, quantifying the majority of GHG associated with commercial buildings. It can be broken down into component metrics, direct and indirect emissions. Direct emissions are emissions from fuel that is directly burned at your building. For example, natural gas that may be combusted to heat your property. Indirect emissions are emissions associated with energy purchased from a utility. For example, emissions associated with the generation of electricity or district steam. To calculate the project's total emissions, first you have to know how much energy the building is using and the different types of energy. Calculating carbon offsets. For LEED, the overall equation is consumption times the CO2 emissions factor equals the GHG emissions, or CO2 equivalent. What you are purchasing is carbon offsets, so you have to determine the total metric tons of CO2 equivalent the building is putting out for both grid-generated electricity and non-electrical energy such as natural gas. This is not difficult to calculate at all. For the calculations, you will need to know the direct and indirect GHG emission factors for different fuel types as defined in the Energy Star Portfolio Manager. These tables are listed in the LEED reference guide. Shown here is a table for direct greenhouse gas emission factors. There are a number of synergies with commissioning because it is the oversight of energy systems. When you look at light pollution, that has an effect on energy. Therefore, it requires commissioning. In optimized energy performance, there's a huge overlap, and then on through any credit related to energy. Remember, when you see these related credits, to think about how things sync up. For instance, how does one decision that affects commissioning also affect minimum indoor air quality performance, etc.? What about ongoing commissioning? These are the same related credits we saw in fundamental commissioning. As you study, try to figure out how each of these fit in. For example, how is it that increased ventilation combines with enhanced commissioning? Think about a project that wants this credit and say, increased ventilation is going to be achieved by a certain fan power, then pulling out through some exhaust fans. Then you would think, well, that would be connected because enhanced commissioning would be looking for those fans on the construction drawings. They might be looking for those fans in the submittal process. This is how commissioning would oversee an actual performance credit. Drawing those parallels is a great way to learn. Anything related to energy is really related to energy performance. You could even see things as distant as heat islands being tied to this, because the heat island effect has to do with how much a building is being heated by the heat retention from the roof. This relates to how much you cool the building, which relates to energy if the building is mechanically cooled. For water reduction, if you reduce the quantity of hot water, you reduce the energy needed to heat the hot water. Your refrigeration choice impacts the energy use. Less efficient refrigerants require more energy to achieve the same level of cooling as more efficient refrigerants. This gotcha is that more efficient refrigerants usually have higher ODP and/or GWP. You must strike a balance based on the project goals. Efficiency can also impact the design of the HVAC system. This concludes the presentation. Thank you for listening.